Okay. So we have just three more classes, and we have. These are all our assignments, and so that's what the final exam is going to be on. Okay, and you have done up to here so far, up to here, and then you have these that are due before the end of before the end of the year, end of the semester. So we're going to talk about higher order derivatives, and we're also going to take a quick look at this section 12.2. So we'll start with that, and then we'll go to, let's see if we've got a different microphone here. Okay, so anyway, let's talk about this first. So, can you read this? Applications of maxima and minima. So you were supposed to study maxima and minima in the homework, and now we want to take a look at example 1 here, which is called minimizing the average cost. So we have a cost function here. So it says here, cost function is, the cost is 2,000 plus 10x plus 0.02x squared. Okay? Now, this is a total, this is a total cost function. So that means if you put in x equals 1, that's the total cost for making one item. If you put in x equals 2, that's the cost of making both items, the first and the second. If you put in 3, it's the cost of making all 3. Okay, so this should be an increasing function, right? If it wasn't increasing, if it was decreasing, right, that would be kind of weird, right? The total cost is getting less, would be a little bit unusual, right? So we don't expect that to be a decreasing function. Okay, now this is for a manufacturer, and they make hockey jerseys, so some kind of shirt. They make kind of shirt, and they're selling it somewhere to college bookstores. And it says in runs of up to 500. I guess what they mean by that is the maximum that they're going to sell to a store is 500. Okay? And this is the cost, the total cost function. Okay, does everyone understand this? Okay, now at the bottom of this there, you see that there's a question. So what does that question say? What are the first 3 words of that question? How many jerseys, how many shirts, right? So that's what we're trying to figure out, how many shirts, right? Now, it's not just, that by itself doesn't make sense. You have to finish the sentence. How many shirts should they produce per run, that means per 500 order, in order to do what? In order to minimize the average cost, right? Okay, now, do we have an expression so far for the average cost? No, we don't. We have an expression for what? The cost, or what I could call it the total cost, okay? So we have an expression for the total cost, but that's not what they ask us about in this question. They ask us about minimizing the average cost. So, first of all, the total cost function is going to have some kind of shape. I don't know what kind of shape it's going to have, but it's going to say. One thing is I do know is that it's not going to look like this. Not going to be decreasing, right? And we already said that. That's the total cost function, not the average cost function. Okay, now, so suppose the total cost function, or no, so now I don't know what the average cost function looks like yet, but it's going to have also some shape. Now suppose it had some shape like this. Okay, suppose it had some shape like that. And suppose this was 500 items. Can you see this, or should I turn the light on? Okay, suppose this was 500. Now the maximum that they're going to sell is how much? 500. It says that they're going to, that's what it means when it says a run of 500. It means the most they're going to sell is 500. Okay? So, and if this is, oh, sorry, no, I drew the wrong picture. Now, if this is the average cost, generally speaking, the firm, the company doesn't want the average cost to be high, right? They want costs to be low. They want profit to be high, but they don't want costs to be high. So where would they like to get the cost? Oops. Does it look like that? Where would they like? Okay, does it look like that? So where would they like the cost to be? Of course, they'd like it to be as low as possible. And in terms of this graph, that would mean they'd like to have the costs here at this level, right? Which means they should produce this amount. Okay, so that's the kind of thing we're searching for. Okay? So we want to find that. Now, we don't have the average cost. So you're supposed to be able to think about it and figure out how to come up with the average cost. But I mean, in this problem, they give us the answer. But in general, you would be supposed to think about it and tell how to get the average cost function. So this function, if we had it, what could we do if we had this function? We could look for its relative, what? Relative minimum and relative maximum, but we're not interested in relative maximum, relative minimum. Right? By the way, I might use the word local minimum because a lot of books use that. Local minimum, relative minimum. Okay? So we want to find the relative minimum, but we need, of course, we need to, I mean, so you learn techniques to do that already. Right? Hopefully you did it in your homework. Okay? So, but we don't have so we need the average cost function first to do it. Now we are given this function, right? So what does the average cost mean? So suppose the cost for if we make 50 shirts, and suppose the cost for 50 shirts is $10,000, then what's the average cost for those 50? It's 10,000 divided by 50, right? So how did we get the average cost? We took the cost function and divided it by the number that we produce. So in other words, the average cost, and we use this notation for average cost. Okay, so anyway, the average cost is the cost divided by x. Okay? And so that's easy to calculate if you have this function, right? Here, you just take this function and divide it by x. So what's the first term when you divide it by x? 2,000 divided by x, right? And what's the second term when you divide it by x? 10. And what's the third term when you divide it by x? 0.2x, right? So that's pretty easy to calculate. And that is the average cost function. So that is right here. So there it is. The average cost is the cost divided by x, and it's here, and it's here. And that's dollars, because cost is in dollars, per jersey. So the average cost is that. Now this looks interesting. The average cost is still a function of x, right? The average cost depends on x according to our calculations. So what does that mean? That means if you produce more, maybe the average cost changes. Now this part says the average cost will increase as x increases, right? But this part says the average cost will decrease as x increases. So together it's going to be the sum of those two factors plus the other factor, the 10, but that doesn't change. Okay? So for different x's, the average cost is different. Okay? Okay, now what is the goal of this problem again? The goal is how many jerseys should they produce to minimize the average cost. So we now have, we want to work on the average cost function. We want to analyze the average cost function. Now we have the average cost function, so we can try to work on it. So let's see how they do that. Now in this language that they do in this problem, there's some terms that we didn't really discuss, because there's another chapter before this, I think it's chapter 7, called linear programming, which we didn't do in this course. We don't have time to do that. And they refer to some of the terminology from linear programming here. But really all you need to understand is this word subject to. So, and also, well, I'm sorry, one more thing. And this thing called these three things. The objective function, that word or words, the constraint, and this word subject to. So you just have to understand those three, that's all. Again, what are we trying to do? What does this say? Minimize the average cost, right? Okay? So the average cost is the thing we're focusing on, right? And we want to either minimize it or maximize it. So the thing that you're trying to minimize or maximize is called what? Can you read that? What does that say? The objective function. So sometimes we're trying to maximize something, for example, profit. So in that case, the objective function would be profit. Okay, sometimes we're trying to maximize, what else might we be trying to maximize? Suppose we had a happiness function, or a work satisfaction function. You know, depended on something like, what can work satisfaction depend on? Money? Salary? Anything else? What about something else? What? I can't hear you.
Vacation.
Vacation, yeah, that's a good one. Number of days of vacation. Anything else? What else can work satisfaction depend on? What else? Oh, that's a big subject, by the way, of study. You know, you can get a PhD in that. But what else could it depend on? Yeah?
Insurance.
Insurance, okay, that's good. But I'm thinking more like sort of social factors, or, I don't know, something else. What else? Like, I don't know, they define all these weird things like probably something like number of groups that you're a member of. I don't know exactly why, but you know, you might say if you're in more groups, then you're more satisfied. I don't know, or maybe the opposite. By the way, there is one study that's interesting about this, and that is it has to do with a field called network theory. And in network theory, they analyze things like groups of people, like, Facebook, you get lots of different groups of people, right? You and your friends, and then other people and their friends. Those are groups or clusters. And turns out that, this is interesting, that people in the workplace who are the connectors between different groups. So we have this kind of, one group here and another group here and another group here in the workplace. And the people who have connections between many groups, they tend to rise much more quickly in terms of their salary and their status in the company. I don't know, that's been shown to be true. So you can aim to do that, be an inter-networker or something like that. I don't know what it would be called. Anyway, so like I said, you could have work satisfaction, and then you might want to maximize that, right? The satisfaction that someone has, right? So you can have lots of different functions, and what are these functions called? What are they called? The objective function. So what is our objective function here in this problem? What is our objective function? What are we trying to either minimize or maximize? So the objective function is always the function that you're trying to minimize or maximize. So in this one, what are we trying to minimize or maximize? The average cost, right? So our objective function is the average cost. Okay, now there's one more word here, and that is the constraint. So we are trying to do something, but we're not like free just to do whatever we want. There are some constraints, and the constraints are going to be expressed about the input variable, or the independent variable, in other words, the x variable. So what is the constraint that we have in this problem? Well, you can read it here. What is it? What does it say? X has to be between 0 and 500, right? And where does that constraint come from? We said that we're only going to produce a maximum of 500, right? So that's where it comes from. Of course, you can't produce less than 0. In fact, they're not even allowing us to produce a 0. Okay? So it's between 0 and 500. So that's called the constraint. Okay? So in chapter 7, where they talk about the subject called linear programming, this is what they talk about. You have an objective function and constraints. And in those functions, in that chapter, this objective function always has to be linear. Now in this chapter, it doesn't have to be linear. So we have a little bit more power here in this method, maybe, than we did in the other, but it's a little different problem actually. But still, we can use the words objective function and constraint. Okay, is this clear? All right, so they write the objective function and the constraint. Now how do we solve this? How do we find the minimum for a function? How do we find the minimum for a function? Well, I hope that we had some problems like that in the homework. What was the technique? Find the derivative. The derivative tells us what? The slope of the function, right? Now, what can we notice about the slope at the minimum? At the relative minimum. The slope is what there? 0. So we want to find the places where the slope is 0. So what does that mean? We take the derivative of the average function, of the average cost, and we want to find out where it's equal to 0. That just means we set it equal to 0 and solve for x. Okay? And that should help us a lot in finding the relative minimum. Okay? Now the one problem is that it doesn't just give us the relative minimum. It also gives us other places where the derivative is 0, gives us the relative maximum as well. So then after we get these places, then we have to decide, is it a relative minimum that we found, or a relative maximum? Okay? So let's see what they say about this. So here's the derivative. So what is it? 2,000 over x squared negative plus 0.02. I mean, 0.2, sorry. Okay? So that's the derivative, and what did we just say we want to do? Find out where the derivative is 0, so we set it equal to 0. When we set this equal to 0, the answer turns out to be plus or minus 100. Okay, that's not too hard to solve that. He says we reject minus 100. Why should I reject minus 100? Because it's not, we don't make negative 100 jerseys, right? Right? So of course we don't consider x equals negative 100. He says it's not in the domain. By the domain, okay, can you guys split up? Split up, move apart. Separate, please. Yeah, the two that were just talking. You two. Yeah, please. Okay. So, this is the actual, the domain, right? X has to be between 0 and 500. So that's the domain. So x equals negative 100 is not in that domain. So we reject that. Okay, so now we're only left with one answer to where the derivative is equal to 0. And that is x equals 100. Now, we still do not know what? We found out where it's flat, where the curve is flat, but we don't know which. We don't know whether it's a maximum there or a minimum, right? So we still don't know that. Okay, so he says, yeah, that's weird. Oh, sorry, okay. Okay, it says we have only one stationary point. I don't know what I did here. X equals 100. The average cost is 50. Oh, I see, okay. Okay, so here's what he does. Okay, ready? We just found a stationary point. Remember, what does stationary point mean? That's where the derivative is 0. Okay, we found only one, and it's at 100, right? Okay, so what does this calculation tell me? If I put 100 into the average cost function, what am I calculating? The average cost of making 100, right? Of making 100 jerseys, and that turns out to be what? Put 100 into the average cost function, which is up here, and apparently you get $50. Okay? So that means what? The average cost of making 100 is 50. So it's flat there. Now, I don't know if that's a minimum or a maximum. So what he says to do, let's look at it. He says the other thing you're supposed to do is check the boundary points of the problem. What are the boundary points, or in other words, the constraints. So what are the boundary points here? X equals what and x equals what? What's the lowest value we allow x to be? 0, right? That's the boundary point. Actually, it's not even allowed. And x equals 500 is the maximum. So what he says is, put in x equals 500 into the average cost function. Okay, so here's the average cost function. Put 500 into that, what do we get? We get $114, according to his calculation. So we'll believe him. Okay, so the average cost for 100 is $50, and the average cost for 500 is 114. So what does that mean to you? So let me put it this way. What I said that we need to find out, we just found that out that at 100, no, sorry, at 50, was it 50 or 100? Where did we get the flat? At 100. Sorry, at 100, we said it was flat. Now, if this is we're trying to decide whether it's a relative minimum or a relative maximum. Okay? Now, there's really only three possible, or four possible shapes. Could look like that, could look like that, could look like that, or it could look like that. Basically, that's all that's possible. Okay? Now, we found out that this is the average cost was 50 here, and we also found that at 500, the average cost was how much? $114. Okay, so I think we only have a few possibilities. We have either this one, right, which would say that this cost was lower than this cost, right? That's one possibility. And the only other possibility is this one, right? Only those two possibilities. So actually, I don't know why he said that. He didn't do 0, did he? He says the only point at which is x equals 0, but that is not, so we have no singular point. So anyway, well, what you could do is you could check, like, what is it here, like at 10? So if it's higher than it is here, then we know the shape is like that. If it's lower than it is here, then we know the shape is like that. So put in 10, let's do that instead. I'm not quite sure what he did actually. But if you put in 10 into the average cost function, that means put in 10 here, what do we get? So we get 2,000 divided by 10 is 200, plus 10, that's 210, plus 2, that's 212, so that's way up here. So that means over at 10, it's way up here. Here, it's over here. So which shape does it have to be? It has to be this shape. Okay, does that make sense? So therefore, we found a relative minimum. Okay, so therefore we know that 100 is a relative minimum. Remember, I didn't know whether it was a relative maximum or a relative minimum, but now I've discovered that it's a relative minimum. So that's the answer to the problem. Okay, does this make sense? Okay. Now, I want to show you another method for doing some of these problems. Well, let's see. Let's go back to a few pages back. And just discuss this method in general. Oh, this is really long, isn't it? Okay. Let's talk about the first derivative test, which is basically what we just did. Okay, the first derivative test gives another very systematic way of checking whether a critical point is a maximum or a minimum. Okay, actually I think I'll go back a bit further. Okay. So maximum and minimum, we discussed this a bit. Relative maximum, relative minimum, relative extrema. What does relative extrema mean? Means either a relative maximum or a relative minimum, right? Okay, good. Okay, so how about this picture? What do we have, if anything? How about I don't know, how about this point here? This is a relative maximum. How about this point here? A relative minimum. How about this point here? Relative maximum. How about this point here? Relative minimum. Let me ask you a question. When we use the technique of setting the derivative equal to 0, is that going to find all of the relative maximums and minimums? Where are the relative maximums and minimums in this picture? Here, 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 and here. What's the slope here? 0. What's the slope here? 0. What's the slope here? 0. But what's the slope here? Nothing. It's not defined. So we won't find this point when we set the derivative equal to 0. Okay, so you have to be aware of that. If you're getting this kind of graph, if you know that it doesn't have this kind of edge here, then you don't have to worry about it. But if you don't know that, then you have to worry about it. Okay? So this kind of edge means what? The derivative doesn't exist here. So that's another place that you generally have to check for. Okay, so you have to check where the derivative is equal to 0, and if there are any places where the derivative doesn't exist. Okay? That's if you want to identify all the possible relative maximums and minimums. Everyone get that? Okay, relative extrema. Let's just read this definition. F has a relative maximum at x equals r, so that means the x value is r, if there is some interval around r, even a very small one, for which f of r, relative maximum, f of r is greater than f of x for every value in that interval. So I discussed that last time, so I won't push it any further, but we did discuss it last time. Okay, let's go on to the next page. Oops, on to the next page. Okay, how about here? Do these have relative maximums anywhere? Yeah. No? Relative maximums? A and B, right? Okay. Some graphs have no absolute extrema of all. Think of this graph, y equals x. What does y equals x look like? It's a 45-degree angle line. So that doesn't have any relative maximums or minimums, right? But this one has a relative minimum, but doesn't have any relative maximum, right? This is a parabola, right? When f does have an absolute maximum, there is only one absolute maximum value of f, but this value may occur at different values of x. What does that mean? Is that confusing or not? It sounds confusing, but when f does have an absolute maximum, there is only one absolute maximum value of f, but it may occur at different values of x. So how about this function here? Does this have an absolute maximum? Yes. What is it? It's this height, right? That's the absolute maximum. But where does it occur? It occurs at more than one value, right? That's what they mean. Okay, it occurs at a and b. Okay? Okay, now let's go on a little more. How do we go about locating extrema? In many cases, we can get a good idea by using graphing technology to zoom in on a maximum or minimum and approximate its coordinates. However, calculus gives us a way to find the exact location of the extrema and at the same time to understand why the graph of a function behaves the way it does. In fact, it is often best to combine the powers of graphing technology with those of calculus, as we shall see. In figure 7, we see the graph from figure 1 once more. So this picture here. Okay? But we have labeled each extreme point as one of 3 types. Okay? So, can you read that or not? Okay. Of one of 2 types. One of 3 types. Notice that 2 extremes occur at the endpoints and the other at interior points. So, what do they mean by that? So they're saying this is an extreme value. It's like the highest value, right? And this they're also saying is an extreme value. Okay, it's the lowest, but I guess these are all the same height. Is that right? Yeah. And the other extreme values are where? 1, 2, 3, 4. Those are, we say those are at interior points. Okay? That is, points other than endpoints. Let us look first at the extrema occurring at interior points. This one, this one, this one, and this one. At the points labeled stationary, the tangent lines to the graph are horizontal. Stationary, stationary, stationary. You can see the tangent lines are horizontal. So stationary points are where the tangent line is horizontal or flat. Anytime f prime equals 0, we say that f has a stationary point at x because the rate of change of f is 0 there. Okay, we talked about that last time. We can call an extremum that occurs at a stationary point a stationary extrema. Okay? In general, to find the exact location of each stationary extrema, we need to solve the equation f prime equals 0. Note that the stationary points are always interior points, as f prime is not defined at the endpoints of the domain. Okay, that's a point that I never made, but let me make it here. The derivative is really not defined at the endpoints. Why not? Because the derivative is a limit. And remember, we talk about limits have to exist from the left and from the right. And you can't come into you don't have anything from the right here, and you don't have anything from the left here. So you can't have a limit here, and you can't have a limit here, so you can't have a derivative there or there. Okay? So the derivative doesn't exist at the endpoints. Therefore, they're not going to be considered stationary points because you can't say the derivative is equal to 0 if the derivative doesn't exist. Okay? Any questions? So in fact, there's no, I'm sorry. Oh, note that stationary points are always interior points, as the derivative is not defined at the endpoints of the domain. There's a relative minimum in figure 7 at x equals q. Right? I don't see x equals q at all. Do you? It's weird. Where is x equals q? There is no x equals q. Oh well. There's relative minimum. There's no horizontal tangent there, so they must be talking about here. Okay? So they say there is a relative minimum here, but there's no horizontal tangent there. In fact, there is no tangent line at all there. F prime of q is not defined. Recall a similar situation, okay, with the absolute value function. When f prime does not exist for some interior point x in the domain of f, we say that f has a singular point at x. So where does f have a singular point? Here, right? I guess this is q. Okay? So you understand? When the derivative doesn't exist, what do we call that? What do we call that point? Singular. Okay? All right. We say that f has a singular point. We call an extremum that occurs at a singular point a singular extrema. The points that are either stationary or singular, we call collectively the critical points. It's so complicated. So many definitions here. But I guess you have to learn them. The remaining two extrema are the endpoints. Okay. So let's just quickly review this one last time. So, what do I call this point? A singular point. And what do I call this point? A stationary point. And what do I call this point? An endpoint. And what do I call all the if a point is either stationary or singular? Stationary or singular, what do I call that kind of point? Critical point. Okay? So actually, okay, so where can the maximums or minimums occur? Where can the maximums or minimums occur? Either at singular points or at stationary points. But what are those called collectively? The critical points. So we can say they occur either at the critical points or the endpoints. Okay, did you get it? You get the terminology? So an extrema can occur either at the critical points, which includes the singular and stationary points, or the endpoints. Okay, so that's the way they express it. All right? Okay, so there we have. Now, this endpoint happens to be the highest value of the function on the entire domain. So therefore we call it what? Absolute maximum, right? Absolute maximum, it's the highest. Okay, whereas this one is only a local or relative maximum. Okay? And this one is relative, relative. And the parent, I guess this is the lowest point. So this is the absolute minimal. Okay? Okay, let's go on. So he says, how can we find the candidates for extrema? So he says, look for stationary points, look for singular points, and look for endpoints. And those are the only possibilities. Now what do we call 1 and 2 together? What are 1 and 2 together called again? Critical points. So we could say look for critical points and endpoints, but that means look for either stationary or singular points and endpoints. Okay? Is this clear? Any questions? Shh. Okay, please stop chatting. Okay. So quick examples. Here's a function. Then to locate the stationary points, what do we, so I can't remember. Stationary means what? Sorry, stationary means what? Singular means what? Endpoint means what? So I forget. Tell me. Stationary means what? Derivative equals 0. Singular means what? Singular means, where's the picture? It's gone. Singular means what? Derivative doesn't exist. And endpoints are endpoints. Everybody knows what endpoints are. So if we want to find it for this function, we want to look in those places. So then to locate the stationary points, we want to find where the derivative equals 0, set the derivative equals 0 and solve for x. So they do that here. So f turns out to be plus or minus 2. Okay? The corresponding points on the graph are negative 2 comma f of negative 2 and 2 comma f of 2. Okay, does that make sense? Which happens to be negative 2 comma 16 and 2 comma negative 16. Okay? So those are the stationary points. Any question about that? Okay, let's do one where we have singular points. Here's a function. What's another way of saying raising to the 1/3 power? What's another way of saying that? Taking the cube root. It's the cube root, like the square root, but the third root. Right? This is the third root. Okay? So this might have a place where the derivative doesn't exist. And that would be a singular point. Let's see what they say. So here's f, so here's f prime. So what rule do you have to use to compute the derivative of this? You need the chain rule, really. But yeah, you need the chain rule. So they use the chain rule here, and this is what they get. Okay? All right, so, which is this, because this has a negative sign, so that we have to put this in the denominator. Okay? So what does that mean? When x equals 1, what happens? Right, it's not defined, right? Right? So the derivative is not, but this is the formula for the derivative. So the derivative is not defined when f equals 1, right? F prime of 1 is not defined. What do we call a place where the derivative is not defined? A singular point, right? What does it look like again? Generally it looks something like this point here, singular point. Okay? So, we found a singular point. So that might be a critical point. That might be a relative minimum or a relative maximum. Okay, so that's, but we haven't, they don't check that yet. Okay, but we did find a singular point. Okay, endpoints, these are the endpoints of any of the domain. Recall that closed intervals contain endpoints, but open intervals do not. Right? Do you understand that? If you have an open interval, the endpoint is not part of the interval, right? So it doesn't contain the endpoint. Okay? If the domain of f is an open interval, Or, if it's the whole real line, we say there are no endpoints. So, of course, if it's the whole real line, there are no endpoints. But even if it's an open domain, there's no endpoints because you can keep getting closer and closer to that value. So they say there's no endpoint. Okay? Now he says, once we have a candidate for an extrema of f, we find the corresponding point, xy, on the graph using y equals f of x. That's what he did over, where was that? Over here. Okay? Yeah. What is this? Okay, how about this? Let's just look at this. Let f of x equal 1 over x. Okay, 1 over x. What does that function look like? That looks like that, right? This is 1 over x, right? Why is that? Because as x gets big, what happens to 1 over x? It gets small, so it goes like this. But when x gets close to 0, what happens to 1 over x? It gets big, and the same thing happens on this side, except it's negative. So it looks like this. Okay, so that's 1 over 1 over x function. Now, what do they do with this? So what is they say, what's the domain for this function? So there's only one place where it's not defined. 1 over x is defined everywhere, except where? At 0. Right? You can't put 0 in, but anything else is okay, right? So what's the domain? Everything, except... Oh, this is weird. What did I mean by that? Oh, I'm sorry. They're giving us they're saying, consider this function, and then restrict the domain even a little bit further. So the biggest domain we could have is the biggest domain would be what? Everything except for 0, right? So one way to write that is from minus infinity to 0, like that. That means everything to negative infinity up to 0, but not including 0. And on the other side, what? From 0 to plus infinity, right? And then this represents a set of points. This is a set of points, all these points here. And this is a set of points, all these points here. So we can use set notation to join them, like that. Okay, so that just means the union of all those points, that's the domain of, that's the biggest possible domain. But in this problem, they're just saying, suppose that we don't have, we're giving even less domain than that. So they say, starting only at 1. So they say what? They say, not this, but this. 1 to infinity. Like that. So it's this one. So that set of points is they're just restricting the domain. So suppose our function is only defined here. Okay? So that's the domain that we have. It's all the way to the left, not 0. That starts at 1 and goes all the way to the right. Now, what about it? So the only endpoint, he says, in the domain occurs where? Only at 1, right? Because negative infinity is not an endpoint. 0 is not an endpoint because it's not included, so it's not an endpoint. And plus infinity isn't. So the only endpoint, they say, is 1. Right? We don't say that positive infinity is a point, so we don't say it's an endpoint. If it's not a point, you don't say it's an endpoint, right? So we don't talk about these as being endpoints. So the only endpoint, he says, is at 1. The corresponding point on the graph, So when x equals 1, what does y equal? 1 over 1 is 1. So is 1 comma 1. The natural domain of 1 over x, on the other hand, has no endpoints. So that's the first domain I gave you, the one at the one below. No, sorry, the one at the top. That domain is called the natural domain. The natural domain means the biggest possible domain we could have. Okay, so I said we can't have any bigger domain than that. We can restrict the domain starting from there. We can make it smaller, but we can't make it bigger than that, right? Because that's everything but 0, and the function isn't defined at 0. Okay, so the natural domain, which is that on the top, has no endpoints, right? There's nothing. No minus infinity and plus infinity are not even points, and 0 is not included, so no endpoints. Okay, any questions about this? Remember though that the three types of points we identify above are only candidates for extrema. It is quite possible, as we shall see, to have a stationary point. Which one is stationary? Stationary is what? Flat. It is quite possible, as we shall see, to have a stationary point or a singular point. Which is singular? Like an edge, right? That is neither a maximum nor a minimum. Okay, we haven't seen that picture yet. It is possible for an endpoint to be neither a maximum nor a minimum, but only in functions whose graphs are rather bizarre. Okay. Now let's look at some examples of finding maxima and minima. So this is how we do it. In all of these examples, we will follow the following procedure. We will use the following procedure. First, we find the derivative y. What's that going to do for us? We want to find the relative maximums and minimums, or just maximums and minimums. So why does the derivative help? Because it tells us where things are flat. That tells us where we have stationary points. It also tells us where we have singular points. Okay, so that's a good thing to look at the derivative and set it equal to, just find the derivative. Next, we make a table listing the x-coordinates of the critical points and the endpoints. Again, what are the critical points? I can't remember. What do we mean by the word critical point again? Which are included in the critical points? The first two, right? So he says, first find the critical points. We make a table of the critical points and the endpoints, okay, together with their y coordinates. So then we're going to know the height at all these important points. And then we should be able to decide where it's highest and where it's lowest. That's the idea. We use this table to make a rough sketch of the graph. From the table and rough sketch, we usually have enough data to be able to say where the extreme points are and what kind they are. Okay, so that's how he suggests we move forward. So let's try it. Here's a function, x squared minus 2x. And he's limiting it. We only have to look between 0 and 4. So where are the endpoints? 0 and 4. Okay, so we already know the endpoints. So if we look at his table, here's his table, I guess. So 0 and 4 are already there. Okay, now we want to see if there are any, what's the general term? I think they're called critical points, and that includes stationary and singular. So we want to look for those. So how do we find the stationary points? We find the derivative and set it equal to 0. The derivative of this is not too hard. It's 2x minus 2. 2x minus 2, set that equal to 0. That's pretty simple. X equals 1. Right? So that is the only stationary point. Right? That's the only place where the derivative is equal to 0. Now we also want to check one last set of points. the singular points, but that means the place where the derivative doesn't exist. But this is the derivative. This exists everywhere, right? It's not dividing by x or square root of a negative number or something like that. So it exists everywhere. So there's no singular points. We found that there was only one stationary point. We found the two endpoints. So we're supposed to make a table of all this. So we have the two endpoints, 0 and 4, and the one, what's it called? Stationary point. The one stationary point at 1. And then we want to see what the height is at each one of these x values. So they put in x into the original function f. So when you put 0 into the original function, what do you get? 0. When you put 1 into the original function, what do you get? -1. When you put 4, you get 16 minus 8 is 8. Okay? So now we know that at all our sort of candidate points, the heights. So the height is what? 0, -1, and 8. So he says now we can use that to make a sketch. So 0, 1, and 4, the heights are 0, -1, and 8. Okay? So we can pretty much be sure that the absolute maximum is where? Yeah, 8, and when I say, okay, I can use the word where and what. So where means where means what value of x, and what means what's the height. Okay, so let me ask you two questions for that. Where is the absolute maximum at 4, and what is the absolute maximum? 8. Okay, so that's just kind of annoying language, but that's the way they do it. Okay, and then the absolute minimum, there's also apparently an absolute minimum, so again I can say, where is it? It's at 1. And what is it? It's -1. And finally, there's a relative maximum. Relative maximum? Well, I'm not sure I'm too happy saying that, but he calls this a relative maximum. Okay? Whatever. Okay. So, you can call it a relative maximum, I guess. A little terminology. Okay. Okay, any questions? Basically, that should be okay. I'm not so happy with that. Calling it a relative maximum. No, it's not a relative. I think that's wrong. Remember what he said by relative extrema? Let's look at that definition again. Here. Look at this. It's wrong. He says f has a relative maximum at somewhere if there's some interval around it, but there's no interval around that point, right? And what was the point again? Pretty sure that's wrong, but whatever. You don't have to worry about it. I'll try not to ask you such a question. There's no interval around this point, right? I can't go over here and over here to draw an interval, so it doesn't seem to be correct to call it a relative maximum. But maybe I didn't read his definition that carefully. Okay, but I don't think most books would call that a relative maximum. Okay, so now he says the first derivative test gives us another way to do this. He says a very systematic way of checking whether a critical point is a maximum or a minimum. So, let's go through this. This is what I wanted to do. To motivate the first derivative test, consider again the critical point at x equals 1 in example 1. Let's go back to that. Okay, here's the relative minimum, right? He says there's another way to make sure that this is a relative minimum. Are you ready? Are you paying attention? It's important. It's not hard, but it's important. If the derivative is 0 here, and the derivative is... Oh, by the way, what is the derivative here? Is it positive or negative? Here, at this point right here. Is the slope positive or negative of the tangent line? Positive, right? What about here? Is the slope positive or negative at this tangent line? Negative. So the derivative here is 0. The derivative here is what again? Positive. The derivative here is what again? Negative. So obviously, if the derivative to the left is negative, and the derivative to the right is positive, and this is flat here, then it has to be a relative minimum, right? 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 And on the other hand, what if it was just the opposite? So if the derivative was positive on the left and negative on the right, then it has to be what? A relative maximum, right? If the derivative was negative, positive here, increasing, flat, and decreasing, then it has to be what? A relative maximum. Okay? That's called the first derivative test. That discussion that we just made. Okay? So let's see that. The first derivative test gives another very systematic way of checking whether a critical point, what's a critical point again? Stationary or singular, right? Okay. Is a maximum or minimum. To motivate the first derivative test, consider again the example 1. If we look at some values of f prime to the left and the right of the critical point, so he does that here, left, and the critical point was 1, to the left of the critical point, to the right of the critical point, you get negative, you get positive, decreasing, flat, increasing, therefore it's a relative minimum. Okay? So here's the first derivative test. Suppose that C is a critical point. Again, what's a critical point? Singular or stationary, of the continuous function f, and that its derivative is defined for x close to and on both sides of C. So, again, the derivative has to be defined on both sides, otherwise you can't talk about it being positive and negative. Then determine the sign of the derivative to the left and right of C. And so, if f prime is positive to the left of C, increasing to the left of C, flat at C and decreasing to the right of C, then what? And it's a maximum. And if other way, it's a minimum. And then there's one other possibility. If the sign is the same for the derivative on both sides, then what does it look like? Then it looks like I drew here. It's increasing, flat, increasing again. That's not a maximum and that's not a minimum. Okay? Or negative, flat, decreasing, negative again. That's also not a maximum. But so that's called the first derivative test. Any questions about that? Okay, so I think I'll end this part here, and I'll go on to here. Higher order derivatives, section 3. Okay, so let's talk about that. Okay, so let's talk about that. So let's go back to an example that we looked at a long time ago, where we have somebody standing at the top of a building, and they have a rock which they're going to drop. Okay, and let's say that the distance that it falls, s, is equal to the distance the rock falls. Okay? And that's measured in meters. In meters. And we'll measure time in seconds. Okay? So, after 1 second, maybe it's fallen to there, and after 2 seconds, maybe it's fallen to there. Okay? And after 3 seconds, it's fallen further. So the distance that it's fallen, s, depends on t, right? So we should write, s depends on t as a function of t, right? Okay, so s depends on t. Okay, now I don't know what the expression is, right? Remember the word we used last week? We used this word, explicit and implicit. So I can say, using one of those words, I can say, I don't know yet the explicit formula, I'm just saying it depends on t. But actually, we do have a formula for it, generally speaking, and we usually say that it's about 9.8 t squared. Okay, so that's supposedly the formula for the distance as t changes. So you know where it is. So after 1 second, according to this formula, where is it? It's at 9.8 meters. It's fallen 9.8 meters. After 2 seconds, where is it? So then you put then you put 2 into t, you get 2 squared, you get 4. So it's 4 times 9.8. Let's say it's 4 times 10, just to make it easy. 4 times 10 is 40, so it's about 40. It's not quite 40, close to 40. And after 3 seconds, just to make it easy, let's use 10 there. After 3 seconds, it's 3 squared, which is 9, so it's 9 times 10, it's 90. So first it's like at about 10 after the first second, then it's at about, 40 after the third second, and then it's like at 90 after the third second. So one thing is that in the first second it only fell 10 meters, but in the second second it fell 30 meters, right, from 10 to 40. And in the third second, it fell 50 meters, approximately. So if it's falling more meters in a second than it was before, its speed must be increasing, right? So the speed is increasing, right? Now, what's the definition of speed or velocity? So let's say velocity, I'll call it v, is what? It's meters per second, right? Right? Meters per second. In other words, it's the change in distance, meters, how many meters, divided by the change in time, how many seconds, right? So that's velocity, generally speaking, right? Okay, so I can ask, what's the average velocity between 0 and 1 seconds? Okay, so that means the distance that it's traveled divided by the time that it took to travel it. So let's say it was 10 and it took 1 second, so what is the average velocity? 10 meters per second. On the other hand, I could also say, what is it between 0 and 2 seconds? In that case, it would have gone, the distance it would have traveled was 40 meters in the 2 seconds. So it's 40 meters over 2 seconds is 40 meters per 2 seconds is 20 meters per second, right? is the average velocity between here and here. So we can calculate the average velocity, right? But we also might be interested in not the average velocity, say, between here and here, but the so-called instantaneous velocity. And so what do we use for that? So that means not what was the average velocity here, but like how fast, if you were sitting right here and you watched it go by, how fast was it going? And what do we use to get that? The derivative. The derivative is similar to the average, but it's when we let the derivative is this. Delta S over delta t limit as delta t goes to 0. Now, we didn't write it that way. We had delta y and delta x, and delta x goes to 0. But for this case, we write it this way, and that is the derivative. That's ds over dt. That's the derivative. Okay, so the derivative tells you the the derivative tells you the instantaneous velocity. Okay, so let's figure out if this is let me change it to here just because I don't want to spend a lot of time doing calculations, let me make it that. So if I want to find s prime of this function, it's obvious, it's very easy. What is it? 20t. So if I ask you, how fast is it going right there? That's at 1 second. T equals 1 second, so how fast is it going? 20. Now what was the average velocity between 0 and 2 seconds? It was 40 over 2, it was 20. So it was going exactly at 20 here, but it was going slower than that here, and faster than that here, and the average was exactly 20. Okay? Any question? Okay, so the derivative gives us the average velocity, the derivative gives us the instantaneous velocity. Okay? Now, what do we call something whose velocity is changing? So if you're in the car and you start at 0, what's that thing we call that I use my foot to press on? What is that called? What is it called? What is it? Yeah, you said it right. What is it? The accelerator. Right? It's called that's what it's called in English. That thing you push your foot on. That's called the accelerator. Okay? So what do we say when something's increasing its velocity? We say it's accelerating. And if it's decreasing its velocity, what do we say? It's decelerating. Okay? So the change in the velocity is the acceleration. Okay? So, what is the change in distance over time? The change in distance over time is called what? The velocity, right? So what about this? The change in velocity over time. That's called the acceleration, right? The acceleration, right? Okay? Okay, now how did we get the instantaneous velocity? We didn't use delta S over delta t. We did the derivative of st, right? So how do we get the instantaneous acceleration? We don't use delta v over delta s. We use the derivative of v dt. Okay? Did I say that wrong? Anyway, we use dv dt. So what is dv dt? Well, where is v of t? This is v, right? That's the velocity. So what's the derivative of that? 20. So what's the acceleration? 20. So does the acceleration depend on t? Do you see a t in here? No. The acceleration doesn't depend on t. The acceleration is constant. that means the acceleration is always the same. It's always 20 meters per second. The speed is increasing by 20 meters per second. Okay, the speed is increasing by 20 meters per second. Okay? That's what the 20 tells us. Okay? Now how did I get to this? I started out with what? With this. How did I get to this? What did I do? I took the derivative of this, and that gave me this. And then what did I do? I took the derivative of this, and that gave me the 20, right? So I took the derivative of the derivative, right? That's called the second derivative of the original function. So the original function was called s, right? Or, no, I guess it was called f. Either way, called s or f. So, sorry, it was called that. So the acceleration, which I'll call a, I'll call the acceleration a. The acceleration is what? F prime of t prime. Right? The derivative of the derivative. Right? But we don't usually write it that way. We usually write it like this. Like that. Okay? So it's the second derivative, it's called. And it's also written like this, by the way. So the 2 goes here, but it also goes here. I don't know, it's just a kind of way of writing it. Okay? So that's called the second derivative. Okay? Now let's just forget about distance and time and just take an arbitrary function and do it again, just to practice with the meaning of the second derivative. So let's take f of x, use x this time, equals x to the 5th. So what's the first derivative? And then if we want the second derivative, we just take the derivative of this, right? So that's written. And what is that? 20x cubed. And then we can also consider the third derivative, which is what? 60x squared. Now if you notice, the powers are decreasing, right? If I keep going, this is usually written with Roman numerals, is 120x, and then if I keep going more, the fifth derivative, I get 120, and then if I keep going, the sixth derivative, 0, the seventh derivative, still 0, and so on. All the ones after that will be 0. Okay, now if I started, my original function was this, what's the derivative of that? Still e to the x, so what's the derivative of that? Second derivative, also e to the x. So it's not getting lower and lower. But when you have a power function like this, it does do that. Okay? So we have what are called higher order derivatives. Okay? And we had some use for at least the second derivative in this case. Right? And that's where it comes from. The notion of second derivative came from this case. This is what Newton did when he was doing physics. That's why he talked about the second, that's why we talk about the second derivative, I think, is what he was trying to work on, which was acceleration. Okay? So we have the second derivative. Now, very quickly, something that's not so easy is the following. Remember, if f prime is greater than 0, that means what? The function is increasing or decreasing? F is increasing, right? Right? If the derivative of a function is positive, that means the function is increasing, right? have to do this quickly. So, now we need to distinguish between two types of shapes. A shape like this and a shape like that. Okay? So this is called concave up, and the other one is called concave down. Okay? Now, which one, sorry. So concave up basically means that you could pour water into it, it would hold the water. Okay? And this one, concave down, means the water would just spill out. Okay? So that's what we mean by concave up and concave down. Another way to say the same thing is here are the tangent lines here, and the tangent lines are here. So we say the tangent, when it's concave up, the tangent lines are below the curve. If it's concave down, the tangent lines are above the curve. That's just another way of recognizing whether it's concave up or concave down. Okay? Now why do I care about concave up and concave down today? Today we were talking about if we have a function and we find out that there's a stationary point here, meaning that it's flat there, we want to decide whether it's a relative minimum or a relative maximum, right? And we had the first derivative test, which said that you check to the left and right, and if it's decreasing, flat, increasing, then it's a relative minimum, and vice versa, it's a relative maximum. Okay? But another way to decide whether it's a relative maximum or minimum is find out the stationary point, and you don't have to check whether it's what it is to the left and to the right, if you check whether it's concave up or concave down. If you have a stationary point and it's concave up, then it's a relative minimum, right? If you have a stationary point and it's concave down, then it's a relative maximum. So if we had a way to figure out whether it was concave up or concave down, then we could do that instead of checking to the left and right. And that turns out to be you can find that out by the second derivative. So let's see why that's true in a very short time. So why does the second derivative tell me whether it's concave up or concave down? Well, if it's concave up, what is happening to the slope? Versus if it's concave down, what is happening to the slope? So what's happening here? The slope is negative, less negative, 0, positive, more positive, more positive. What's happening if it's concave down? The slope is positive, less positive, 0, negative, more negative, more negative. So in which case is the slope increasing as we move from the left to the right? Here, the slope is increasing as we move from the left to the right, right? It's negative, going flat, and positive. That's called increasing. So when the slope, the key word is the slope, not the function, right? When the slope is increasing, it's concave up. When the slope is decreasing, it's concave down. Now, we also made this statement. This is a different statement. This is just a statement that says that if the derivative is positive, then f is increasing, right? Everyone agree with that? Now I'm going to do something a little bit tricky now. Okay? What I'm going to say is, this is true no matter what I put in here, no matter what function. So I could put, egg. It doesn't make any sense, but I could say, if the derivative of egg is positive, that means what? Egg is increasing, right? So it doesn't matter what I put in there, right? You agree or not? Okay? So I'm going to put something special in there, and that will prove my point about that the second derivative will tell us about whether it's concave up or concave down. Okay, does everyone agree? Let's read it one more time. If the derivative is positive, the function is increasing. Or, more generally, if the derivative of whatever we put in there is positive, then the original thing is increasing. Right? Everyone agree? Okay, now here's what I'm going to put in for the original thing. Okay, ready? Here's what I'm going to put in for the original thing. It's not going to be egg. It's going to be this. This is the original thing. So it's tricky. So what does that mean goes here? Egg here means the derivative of egg goes here, right? F here means the derivative of f goes here. F prime here means what? The derivative of f prime goes here, right? So that's f prime prime right? So what does it say? If the second derivative is positive, then what? Then f prime is increasing. But if f prime is increasing, which one of these has f prime increasing? This one? No. Here f prime is decreasing. Which one has f prime increasing? This one, concave up. So if the second derivative is positive, f prime is increasing, but if f prime is increasing, we get concave up, right? But why did we care if it's concave up or down? Because we said, if we know that it's flat somewhere, we don't want to do the first derivative test, right? Why did we care if it's concave up or down? Because we want to use the so-called second derivative test instead of the first derivative test to find out whether it's a relative maximum or minimum. So what do? We check where is it flat, and then at that point we check the second derivative. If the second derivative is positive, we know it's concave up, we know it has this shape, therefore it's a relative minimum. Okay? On the other hand, if we find that it's flat here, but we find that the second derivative is negative, then it's going to be, this is decreasing, then it's going to be concave down. And if it's concave down, it means it looks like that, therefore it's a relative maximum. And that's called the second derivative test. So what's the second derivative test again? You check the first derivative, that gives you the potential points for maximums and minimums, and then you look at the second derivative at each of those places to tell you whether it's a maximum or minimum. Now there's one other possibility, there's one other thing we have to talk about. And if we have this shape, this point is called an inflection point. So an inflection point is where it changes concavity. Right? Isn't this where it changes concavity? What is it to the left of here? What concavity does it have? Up or down? Up. To the right of here, what concavity does it have? Down. So it changed concavity here, somewhere. So that place where it changes concavity is called an inflection point. And there, generally the derivative, the second derivative will be equal to 0. So to find, because remember, if the second derivative is negative, it's what? Negative, it's concave up. So here it's negative, here it's positive, and in between negative and positive is 0. Second derivative is 0. Okay? So that's called an inflection point. Now the opposite is not necessarily true. If the second derivative is 0, doesn't mean that you have an inflection point, because you could get something that looks like this. So it goes like that, and then it sort of looks like it's going to change concavity, but then it keeps going. Okay, so you get that it's the second derivative is 0 here, but then it doesn't switch over to the other direction. So just because, so this is not true. This direction, that is, if this is 0, it doesn't mean you have an inflection point. But if you have an inflection point it means that the second derivative is 0, I think, unless I forgot something. Okay, yes? Inflection point? No, not really. It has to do with just trying to make a graph of the function. So if you're trying to graph the function, you also would like to know where the inflection points are. Okay? But no, it doesn't have anything to do with maximums or minimums. Okay? Okay, that's all we had time for. As I said, usually I'll spend 4 times as long on any particular subject than we get to spend here. So it usually means like in another class where we have much more time. So I have to rush through this. I really don't like to do that at all. No, I really hate to do it, but I don't know. So I sort of have to leave it to you to read the text, which usually I don't think that's fair, but fair or not, that's the way it has to be. Okay. All right, anyway, so you have some more homework due, so please make sure that you get it done. So unfortunately, I didn't cover elasticity at all. So maybe I'll take that out. In fact, I'll do that right now. I'll make that for the following week, not for this week.